Section 4.3 is linearly independent sets or bases. So we're going to talk about sort of a concept that's been in the background for a while, and it's something that we've probably touched up against many times. It's probably something that has possibly even occurred to you as you've worked on sections preceding this. And what that really is this idea of we have the span of a set of vectors, and then we have a question about whether or not these vectors are linearly independent. So the section starts off with just a quick reminder of the definition of linearly dependent vectors and linearly independent vectors. Not a bad reminder, but we've done that fairly recently, so we don't really need to dig into that too deeply. Just recall that vectors are linearly independent if and only, if and only if the only solutions to this equation, in other words, the only constants C1 through CK for this equation that hold are when all of the C's are 0. So that's only the trivial solution. That's what I just described there. So this is linearly dependent, right? That's when one of the C's, at least one C in this combination, is not 0. So at least one of these constants, one of these weights is not 0 in this linear combination. Down here is linearly independent. So if I take care to read it correctly, then we see that that we have the same old linear dependence and linear independence equation for each of these, or condition for a set of vectors. Now, we can talk about a space like R3 being spanned by vectors. And we've seen that, well, it looks like it took 3 vectors to span R3 most of the time when we would consider that. And sometimes maybe we'd have more than 3 vectors and we could span R3. But the question really starts to come up: how many vectors do you need to span a certain space? So this is putting us on our way to answering that question. So we just need to put together a couple quick facts about sets of linearly independent vectors. So the first theorem that we come across in this section is that a set consisting of a single vector V in a vector space V is linearly dependent if and only if V equals 0. So if we have a single vector in a set, and that set is linearly dependent, the only way that can be the case is if V is equal to 0. So this really, so any set containing a single non-zero vector is linearly independent. All right, so the intuition behind the proof of this theorem, or at least just the intuition behind this theorem, is the following. Suppose we have a vector U, and then we have some linear combination of this vector U that's equal to the 0 vector. Okay, so this is if we have just one vector in our set, then and we have this relationship, right? This comes from the previous page that we wrote down. Right? This comes from this equation right here. In either case, it's the same equation, right? So we're writing that down as if we're going one way or the other. Well, the only way that this is true is if C is 0, which tells me that it's only the trivial solution, or if C has to be 0 for this to be true, then we know that that's a linearly independent case, and we know, or otherwise, if the vector U is 0, well then C can be any value we want it to, because we'll still have a 0 here, so C could be equal to 1 potentially. So that, of course, then U has to be the 0 vector. So one of these two things happens. If C is equal to 0 necessarily, well, then we know that we're linearly independent. So we have a non-zero vector U, or the vector U is 0, and well, then we see that we can pick some non-zero C, and we're linearly dependent. So that's basically the essence of that theorem. So the second theorem is we let V1 through Vk be a set of at least 2 vectors in a vector space V. So maybe it's just V1, V2, but there are at least 2 vectors in this set. And then this general set V1 to Vk of at least 2 vectors is linearly independent if and only if at least one of the vectors in the set can be expressed as a linear combination of the others. So let's think about this in regards to linearly dependent. If this set is linearly dependent, or if we were to state that this set is linearly dependent, well, that's true if and only if there exists scalars x1 to xk, not all of which are 0, such that this equation holds. So that's from the previous page. I've used x1 through xk instead of c1 through ck, but those are still just scalars, constants, not all of which are 0 because this is equivalent to these vectors being linearly dependent. Well, we can solve for one of these. Say x1 is non-zero, and if that's not the case, then we could relabel and make it that v1 and x1 are the labeled pair with an x1 that's not equal to 0. So we're just sort of not keeping it as general as possible by choosing x1 to be 0, but we could make that the case by relabeling all our vectors. So nonetheless, if x1 is non-zero, then we can solve for v1 in this expression, and we have that v1 is equal to this linear combination of the other vectors, right? We have a constant times v2 up through a constant times vk. These are all added together, and we get v1 out of that. So v1 can be expressed as a linear combination of all the other vectors in this set, if and only if this set of vectors is linearly dependent. And again, we're having some flexibility with v1. We can relabel the vectors to make whichever one has a non-zero weight in front of it, the vector v1. So let's see some explicit examples here for a moment. We're asked to determine if the given sets are linearly independent or linearly dependent. Remember, a pretty quick way to figure this out is to just take the two vectors that were given, or however many vectors we are given, write them as the columns in a matrix, put that matrix into row echelon form, and then look for free variables. If you have a free variable, then you have a non-trivial solution to the homogeneous equation, which means you have a linearly dependent set of vectors. In this case, we have an entry, leading entry in every row, so we don't have, sorry, we have a leading entry in every column. So we have no columns that don't have a leading entry in it. So that means we have no free variables. We have no free variables. We have a linearly independent set of columns. We have no solutions, no non-trivial solutions to the homogeneous equation. So an echelon form with a leading entry in every row gives us a linearly independent set of vectors. Okay, we do the same for the second set, and we arrive at, through row echelon form, we arrive at this row echelon form here. Now this one, again, don't let the row of zeros bother you, right? We have a leading entry in each row. We have no free variables still. We have no non-trivial solutions to the homogeneous system, right? Remember, we're not adding it a lot of times now, but where this highlighter is, we've got a column of zeros there. Back substitution tells me x2 is 0. This is x1 and x2 combined in some way equal to 0. So x1 is going to have to be 0. And that's only the trivial solution. We have exactly one solution, and it's the trivial solution to the homogeneous problem. So in both cases, we had linearly independent vectors. Now, one way we could change this could be a linearly dependent set. And you can see that if you change this 9, I believe, to a negative, that might do it. Is that what was not coming out initially? Potentially. So I'll just leave that. The book, I think, has a nice example of a linearly dependent case. Remember, all you would be looking for the linear dependence case is to find a column that doesn't have a leading entry or a pivot position in it. And then you've got your free variable, which means you have infinitely many solutions, which means you have some non-zero or non-trivial solutions. So we're given 3 polynomials, P1, P2, and P3 here, all different combinations of constant through x and x squared. And we're asked, is the set P1, P2, P3 linearly independent or linearly dependent? So don't panic when we see something that is in vectors here, and we're asked to determine whether or not we have linear independence or dependence among the set. The same expression still holds, right? So what we're asking is it true that there exist A, B, and C and R, so scalars, 3 scalars, 1 scalar for each of our polynomials, P1, P2, and P3, such that A times P1 plus B times P2 plus C times P3 equals 0. And what we're asking is, are they not all, is it true that they exist and they're not all 0? Can we find a set of these 3 scalars for which one of them is not 0? If not, well, then we know they're linearly independent. If we can, if there's some A, B, or C, at least one of those being non-zero, then we know that this is a linearly dependent set. Now, this is a nice way to write this. It looks just like the rehashed definitions on the first page of these notes, except maybe the P1, P2, P3 don't have vector arrows over the top of them. But if you drew that in, you'd probably feel a little bit more comfortable with the appearance of this situation. Polynomials can be treated as vectors, essentially, the way we're doing it, or at least the way we're looking at them in this problem. So let's fill in the details. P1 is this, so there's A times P1. And then same for B, B times P2. P2 is this expression. So we have B times P2 here. We do the same for C times P3. And we have this long polynomial here. Now we combine the like terms, the like coefficients. If you recall partial fraction decomposition, maybe from Calc 2, maybe from other places, this looks a lot like partial fraction decomposition for decomposing improper rational functions. So, or proper rational functions, I should say. So now for each of these coefficients, in order for this whole equation to be equal to 0 on the right-hand side, right, the left-hand side to be equal to 0, we need each of the coefficients to be 0. So that gives me a system of 3 equations. The first coefficient being 0, the second coefficient being 0, and the third coefficient being 0. Well, now when I look at this, I realize I have a linear system of equations. So I write that as its augmented matrix. I put it into row echelon form, row echelon sufficient, right? And then I scan through this, and I'm interested to see whether or not I'm not so much going to scan the rows as much as I'll scan the columns. This one has a pivot position. This one has a pivot position. This one does not. So C, the variable C in this now, or the unknown parameter C, or the unknown weight C here, is a free variable, which means we have infinitely many solutions to this equation right here. We didn't find any of it. Well, we didn't find any because we haven't picked a value for C, and we haven't written down what A and B are in terms of C, but we could do that. We could easily do that. But we don't need to, because we know that we have a free variable. C is free, so we know that the columns are linearly dependent in this matrix. If the columns of this matrix are linearly dependent, then these polynomials are linearly dependent, right? So each of these polynomials are more or less acting as columns. P1, P2, and P3 are the columns of this. And if you kind of try to trace this out, you'll see where that's the case. I believe this is the x squared coefficient column. This is the x coefficient column, and this is the constant coefficient column. So that's why it makes sense to view polynomials potentially as column vectors as well. So yeah, these polynomials are linearly dependent. If you look closely at these 3 polynomials, you can actually see a linear dependence relation in them if you give it just a moment's thought. Take 1/2 times P3 and you get x, and then do 3 times P1 and you'll get 6 minus 3x squared. So add, maybe I'll just write it down. You could say this at the very end, 3 times P1 plus 1/2 times P3 equals P2. We're able to form P2 by taking 3 times P1. If you write down the details to that in terms of the the polynomial, the actual polynomials themselves in terms of x, you'll see that this is in fact true. So that's another way to see that you have linearly dependent vectors. We can write P2 as a linear combination of the other two polynomials in this set. But that's harder to see. To come up with one of these out of thin air only works when we have relatively simple looking objects here, polynomials. These aren't that simple, but they're simple enough to have done it. These linear combinations can be quite a bit more complicated. This method outlined below, getting to an augmented matrix, is always recommended. So that leads us to this notion of a basis, right? So we've kind of worked with linear independence again. We can talk about the linearly independent columns of a matrix. And something you might notice about this is the following. These two highlighted columns, we could use these two columns to generate this column. Of course, after all, that's all we were really doing up here anyway, was we were using the coefficients of these we're using multiples of these polynomials against their coefficients in order to generate another one, or one from the other two, right? So in other words, when these polynomials are represented along their coefficient columns, we're just trying to combine one polynomial with another polynomial, or in other words, one column with another column in order to get the other columns. When we look at these columns here, we can zero this 3 out. If we do a column operation, right, we can zero that 3 out. So we have 1, 0, 0, 0, 1, 0, and I could generate 0, 2, 0 from the vector 0, 1, 0 by multiplying it by 2. So I just spoke through a linear combination there, but we don't need this vector anymore. It doesn't, in the sense of generating column space for this matrix, because it's redundant. It doesn't generate anything new. So that's what we're trying to get at with this idea of a basis. So rather than write down these three vectors that I was just talking through, let's see, 1, 0, 0, 3, 1, 0, right? And then this vector, the last one was 0, 2, 0. I could just as well span the same set with this set of vectors as I could with this set of vectors. And really on the flip side, I could have chosen another one. I could have chosen the this vector to keep and throw the middle one away, but either way we can get there. And I'll challenge you to come up with a linear combination that of these two vectors that forms the third right here. It shouldn't be too hard to come up with. It's probably -3 times the first vector plus the second. And then I'll let you finish the rest of that to get this vector from that linear combination. So yeah, so then the question is this: if these are both of these sets, this span and this linear span, each of these are the same subspace, right? Because they're equal to each other. Now, well, how do we know when to stop? And this is exactly what the basis tells us, the definition of a basis. So if H is a subspace of a vector space V, a set of vectors, script B we have here, V1 through VK, and V is called a basis for H. So for H, the subspace, the basis for H, if B is linearly independent, so all the vectors in this set B are linearly independent, right, of each other, and the subspace spanned by B coincides with H. In other words, H is equal to the span of B, or the span of all the vectors V1 through VK. So that's the key thing that we've been close to so many times without really talking about it explicitly. If we look at these two vectors, we only have two vectors. Remember that to consider whether or not two vectors are linearly independent as a set together, all we need to look at is inspect to see whether or not one is a scalar multiple of the other. And these two certainly are not scalar multiples of each other. So they are linearly independent. So this actually would form a basis for the null space of this matrix here, right? Since I pulled it from that example. So that's a basis for the null space of that matrix. I know that the matrix wasn't originally from a question about a null space, but so there we go. Now, let's see. So we can move on from there and let's have a look at some examples and some results concerning this. So first, it'll be somewhat straightforward, just talking about examples of these bases. But if we have that A is an invertible n by n matrix, then the columns of A span Rn. Well, I guess this should not say that the columns of A span Rn. The columns of A are a basis for Rn because they are linearly independent and they span Rn. Both of these facts come about by the invertible matrix theorem. So the language there kind of got me for a minute. Columns of A form a basis. Form a basis for Rn. And that's what I wrote down below as well. I finished the thought, didn't catch the error before. Yeah, the invertible matrix theorem gives us the fact that the columns, if you go back and look at that theorem in chapter 2, I believe, then it tells us both of these things, that the columns are linearly independent and that the columns span Rn. So yeah, there it is. We have a basis whenever we're dealing with an invertible matrix A, n by n invertible matrix A. So the standard basis vectors of Rn, remember E1 through En, they form a basis for Rn. Okay, the easiest way to see that is to write E1 through En, form the matrix that, or write them in order to form their n by n matrix, which happens to be the identity matrix, which is the echelon, reduced echelon form matrix. Remember that it's an invertible matrix. You take its determinant, it's 1, which is non-zero. So its columns are linearly independent and they also span Rn, just like, or basically by the fact of what we saw above, right? When we're dealing with an invertible matrix, we have that its columns are a basis for the space Rn for dealing with an n by n matrix. So this is something we're always kind of thinking about, that unique solution to a system of equations when we row reduced a matrix and got to something that looked like this, where we have a unique solution that comes out. This is also a matrix with a non-zero determinant. And now this is also a matrix whose columns form a basis for R, in this case, R3, since it's a 3 by 3 matrix. This is one all sort of connected idea now. It's just another version of what we've worked on up until now. So it's nice that we keep expanding from where we know and just looking at essentially an equivalent idea in so many cases. Just to see the work that we did in this example, determine whether or not these vectors are a basis for R3. Well, the idea is to see whether or not they're linearly independent and to see whether or not they span R3. Well, let's confirm that. I guess that maybe the easiest way to do that, I mean, let's just work through it, I guess, first now. Let's see, so to put it in a row, so I put my vectors in, I write them as columns, and I'm going to put my matrix into row echelon form, and that's what we did right here. Well, remember, if we were going to take the determinant, so the operations we do, maybe I would have divided by constants or multiplied by constants or something, factored a constant out for the determinant. Maybe I would have swapped rows somewhere, something like that. I'd have to be careful with my multiples or minus signs out front, but I would never, if this matrix has non-zero determinant, then so will a row equivalent matrix to it. There's no way to get a factor of a 0 out because I would be factoring a 0 out of a row, which means I'd be dividing a row by 0 to multiply the front of the matrix by 0, and that's just undefined. So if a matrix has a non-zero determinant, then any matrix that it's row equivalent to will also have a non-zero determinant. So keep in mind that they won't have the same determinant. This matrix does not have the same determinant as this matrix necessarily. It might coincidentally, but that's generally not the case. But if one is non-zero, the other one will be non-zero. So that's probably simple enough, but that's the argument that ends it for us. However, if we look more deeply at this, just to get some more intuition about it, we notice that all columns have a basic variable in them, or a pivot position. So there's no free variable. So our columns are linearly independent. That's one requirement for these columns to be a basis for R3. The other one is that they span R3. Well, the way to tell this really is to see that every row has a leading entry or a pivot position in it. So we look along the rows and we see that, okay, well, we have a leading entry in every row, and this means that the vectors span R3. Okay, so why is that? Remember that was hashed out back in chapter 1 with I believe it's called the Equivalence Theorem back then. At this point, we've got a few named theorems, and it's easy to forget them, but that comes out of the Equivalence Theorem, and that does it. But again, we didn't need to go into these details like we did. I'm just connecting it back to things we've already worked with. We didn't need to go there because we looked at this and realized, well, we have a non-zero determinant. We have an invertible matrix. The matrix is invertible, so we know that this is going to form a basis. So again, there are multiple ways to make our deductions and with these problems, and that's a really nice kind of landscape to be in. So the spanning set theorem. So this is a nice result concerning the set of vectors S, V1 through Vk, and we're going to talk about its span, H. So if one of the vectors in S, say Vi, is a linear combination of the remaining vectors in S, then the set formed from S by removing Vi still spans H. So in other words, if I go in here and say, okay, I'm going to pull Vi, or maybe I'll say V1, take V1 out of this set, just remove it, because it happens to be a linear combination of V2 through Vk. Well, then I'll still get every vector I could possibly try to generate by spanning V2 through Vk, because I know that I can already generate V1. So we see down below, let me read through the details of this portion of the proof that I put together. This is part A, right? So we let H be the span of V1 through Vk. We suppose a vector V1, if necessary, we'll just relabel, right? I'm assuming that V1 can be written as a linear combination of the other vectors. If that's not the case, just like we did before, then we could relabel them all so that V1 is such a vector as this. You know, if it happened that V4 was the vector that could be written in this form, then I could just rename it to be V1. But anyway, this is just agonizing over the name of something. So suppose V1 could be written as a linear combination. Well, if that's the case, then any vector U in H is a linear combination of all of V1 through Vk. So I can write that down. And well, what I realize is this. Well, V1, I don't need V1's information. I can form V1 with this recipe here. So let me make that substitution. And what we see down here is that, well, here's U, the vector, any vector in our span of S, or our set H, which is equal to the span of S. Any vector U, right? That's an arbitrary U in there. It can be written in this form, but I can substitute out for V1 with this linear combination of V2 through Vk. And when I do that, here's A1 times my V1 that was right here, and that's this. Oops, that's this piece, this expression. That's substituted in down here. And when I look at my expression for U1 right now, at this point, I probably realize that nothing involves V2. So I'm free to omit V1 from my set S, and I can have the span H be equal to the span of V2 through Vk, and I can still generate everything I could as I would have with V1 through Vk instead of V2 through Vk, because I don't need V1 because I can generate it with V2 through Vk. So that's, you know, and this is just the official details of that finished up. Here's grouping like coefficients in front of each vector, right? Like terms or whatever. So we see that U can be written as a linear combination of just the vectors V2 and VK. So that means that U is in the span of this smaller subset, seemingly smaller subset, V2 through VK, rather than all of V1 through VK. So in other words, if U is in H, if U is in this set, and all these conditions are true, then U is still in this set. So I don't need V1, I can toss that one out and still generate the whole space. So that's how we get this equality. That H is still equal to, I should finish that note off right here, so that H is equal to the span of the lesser collection, V2 through VK. There we are. Now, the second part of the theorem says this. If H is a set of vectors that is not just the zero vector, so in other words, H is a set that contains a non-zero vector, then some subset of S is a basis for H. Okay, so if H contains any non-zero vector whatsoever, right? Then S, right, is composed of these vectors. We can use property A to get rid of vectors that are linear combinations of other vectors. And we can keep paring these down and to at least the point where there's only one vector that's left, but H is not just the zero vector. So the single vector that's left would have to be a non-zero vector if we do get down to just one vector. And in that way, we could show that, yeah, some subset of S, namely that one we just narrowed it down to, is in fact a basis for H. Okay, so we're guaranteed that we can find a basis for H is the way to say this, right? So in other words, as long as this space is not just the set containing the zero vector, we can throw away redundant vectors until we arrive at just a true basis for H, right? And the idea there, to go back to an example, is this. If I wrote all, maybe this is not the right one. I need all of these on a separate page. Aha, here's a good one. If I wrote this, so H is equal to this span, right? Well, what I'm able to do, what that theorem is telling us we can officially do, is the thing that we did essentially unofficially, is over here, looking at these two vectors, I can still span, H is still equal to both of these, right? So H was equal to this original span. Well, I don't need all those vectors. I can throw this one away. And here I've got, I'm down to just these two vectors, right? Also, H is some non-zero, a set with at least one non-zero vector in it, which means that there is some subset of these vectors here, some subset, right? Could be all of them. In this case, it's not all of them, but some subset is a basis for H, right? So this one's not a basis because it's linearly independent, or it has a linearly dependent column, right, among them. However, this one is a basis because they're linearly independent. And that's just telling us that, yeah, we can find among these vectors a subset which are linearly independent and still span H. In other words, we can find a basis for H in there. So it's maybe a lot of to do getting the result together and kind of hashing through it, but it's nice to know that to have this fact guaranteed to us that we can form bases for sets in this way. So another example is the following. We let A be this 3x4 matrix, and we let V1 and V2 be the two given vectors that we have here. We're asked to show that V1, V2 is a basis for the null space of A. So we get to work on this, maybe one thing we want to check is we want to have a look at A's row echelon form. When we do that, we see two columns with basic variables, and we see two columns that suggest free variables, right? So if I have two columns that have free variables, well, then I'm going to have two vectors in the null space of this thing, right? The null space is not really what we're looking for directly. We're a little bit more worried about what is spanned by these things. But these two vectors here, if we look kind of closely again, we realize that we could generate. So if I wrote these two vectors down, 1, 0, 0, and 1, -5, 0, we could do, I could use 1, 0, 0. Essentially, if I wrote this in reduced echelon form, and this was a 0 here, and this became a 1, -5 became a 1, I'd have 1, 0, 0, 0, 1, 0. And we could generate both of the second columns over here with either of these two 1, 0, 0, 0, 1, 0, or the E1, E2 vectors for R3, right? And that would be sufficient to generate either one of these. Well, what turns out to be the case is that these columns that don't have a pivot point or pivot position in them, or a leading entry in them, don't contribute anything to the span. They're linearly dependent on the other vectors. So they get omitted, and that's just that. So we see that we'll have two vectors for our span, right, for the linear combinations of this. So what we want to check is that these two vectors here are, in fact, component or a basis for the null space of A. So the first thing we want to see is that they're actually even in the null space of A, right? So we see that AV, if we do that product, write it all out, times this 4×1 vector, you'll see that yes, you do get the 0 vector. It'll be a vector of 3 zeros. And similarly for A times V2, you'll see it'll be a vector of 3 zeros as well. So they are both, in fact, in the null space of A. So that's good. And we expect there to be two vectors. Another way to see that is that x3 is free and x4 is free. And when we were to write our solution out, we would split up. I know that x2 hasn't been solved here, but it could in terms of x3 along this. So we would write x1 and x2 in terms of x3 and x4, and we would write down our solutions to this homogeneous problem as the parameter x3 times a vector and the parameter x4 times a vector. And what we'd end up with are these two vectors that make up the null space, right? Whose linear combinations make up the null space of this matrix. Well, we see two vectors in front of us that are elements of the null space. They couldn't be the span so long as they're linearly independent. So we need to check if they're linearly independent. Well, the good news is we have two vectors. So all we have to check is to see whether or not there's a constant C for which we can multiply it times V1 to get V2. And I think by quick visual inspection, we'll see that no such constant exists. So the last line here is that there's no constant, there's no scalar in the real numbers for which this is true. Thus, these two vectors are linearly independent. So this set is a basis for the null space of A. We know that we only needed two vectors to span the null space, right? Because that's, here we've got the null space written, or nearly in solution form with x3 and x4. So we need two, and then we find two that are in the null space and are also linearly independent. So that's sufficient to be a basis for the null space. So a little bit of work moving around to get that, but really we utilized, again, nearly writing out this solution, but at least identifying the number of free variables, so that way we would know the number of vectors that would be in our null space. Okay, so find a basis for the column space of A. So we'll take our row echelon form and take it one step further to reduced row echelon form. And look, I didn't finish with the details of this if at least that first row, second or third and fourth column comes out to, because it doesn't really matter. When I look at this column and this column, I realize that I can generate anything in this vector or this vector in that entry by a multiple of the first column. Similarly, I can use it, in a linear combination of this vector and this vector. I can generate either this column vector or this other column vector, no matter what it is, right? These are the standard basis vectors. There we can generate pretty much anything with these two vectors that has a 0 down here. That's what these two vectors have. So the only two vectors I need from this are the first two. They're the linearly independent ones. And we've seen that the other two are spanned by these two. So the last thing we want to be sure of is that these two vectors are linearly independent. Well, it's pretty obvious they're linearly independent. They're two vectors. They're not scalar multiples of each other, so they are linearly independent. So now we have two vectors which span the column space of A. Again, these would be the 4 columns of A, but we throw away the last two because they can be generated. They're linearly dependent on the first two. So our basis for the column space of A is simply these two vectors right here. Okay, we'll have cleaner methods to get to this as we move on. Most notably, we'll have a dimension theorem or a rank theorem for matrices, and that will really help to cement a clean technique for finding this. But for now, key things are finding columns with pivot positions, identifying columns with free variables without pivot positions, and potentially putting things in a reduced echelon form to figure out. And really, if you put things into reduced echelon form, you're only going to keep the standard basis vectors, right? You might not get all the standard basis vectors. Here we didn't. You might not get, so this could have been 0, 0, 1 for the second standard basis vector. We might have skipped 0, 1, 0. So multiple things are possible here. So a couple theorems. The pivot columns of a matrix A form a basis for the column space of A. Okay, so this is kind of what we were doing, but with a lot of legwork on the previous page. So we won't have to work so hard in the future thanks to this theorem right here. So we could go back and look at the previous example. The pivot columns of a matrix A form a basis for the column space of A. Well, that's exactly what we ended up doing here, right? Here's a pivot column. Here's a pivot column for this matrix. And that's it. There are no more pivot columns because we don't have any more pivot positions in a column. So we pick up these column vectors and they're going to form the basis for our space. We just did a lot of arguing as to why that's the case. There is a nice or reasonable proof to this in the textbook. Here's just a bit of intuition for it. If we have a matrix A of this form, and then its row equivalent to something in reduced echelon form that looks like this, well, we know the following. We know that for this column, it's linearly independent of anything that follows, because when we move to the second column, it has a non-zero entry in a place where this one has a 0 entry and then zeros everywhere else, right? They're not multiples of each other. So we can move pairwise along this and realize none of these vectors are linear combinations or a multiple of the vector before it. And as we proceed, we can see that none of the vectors after this are linear combinations of one that precedes it. Now, eventually we might get to something that looks like this. So imagine we just have, similar to what we had in the last example, we just have this vector, and this is the third and last vector, and it's just a couple numbers where there are asterisks here, and we have a 0 down there. Well, this vector can be generated by linear combination of these two vectors sufficiently, and so this is a linearly dependent vector, so it gets thrown out, right? We don't need it in the basis because it's already in the span of these two pivot columns that we've already picked up. So it's redundant information, so we don't collect columns without pivot positions in them. And we know that the columns with pivot positions in them are linearly independent because, well, another way to put it, if they're in reduced echelon form, they're standard basis vectors. And as standard basis vectors, they're just not. We just know that they're linearly independent. And remember that if we write down all the standard basis vectors for a space for Rn, then we form the identity matrix In, and we know that that thing's invertible. We know that it has all linearly independent columns thanks to that. That's one way to think about it. And then any subset of a set of linearly independent vectors is also linearly independent. So that would be, so if we didn't get all of our standard basis vectors here, then we could use that fact or argue along those lines to show that these must be linearly independent. So the last bit of this too is to say, well, if B has these this matrix has these linearly independent columns, then how do I know that that translates to A? Well, remember, linear independence is really just concerning ourselves with the homogeneous equations, AX equals 0 and BX equals 0. Well, remember that row equivalent matrices have equivalent solutions to these homogeneous equations or to any equations. So this is the case here, right? The columns of A and the columns of B. So they satisfy the same, they have the same linear independences and the same linear dependencies. So they share, essentially, thanks to that, they share bases. So if B has a linear dependence, then A has the exact same linear dependence. And similarly, if A has a linear independence, B has the exact same one because they have the same solutions to their homogeneous equations. So then we know that what we can do with this is take the matrix A, put it into its echelon form, pick up all its pivot columns, and we now have a basis for it. That works out quite nicely. Now, if two matrices A and B are row equivalent, then their row spaces are the same. So this is similar to what we were just saying above. They're row equivalent, then the row operations away from each other. But the theorem's concluding that their row spaces are the same. We'll see that in just a moment. If B is in row echelon form, the non-zero rows of B can form a basis for the row space of A as well as for that of B. So if B is in echelon form, the non-zero rows of B can form a basis for the row space of A as well as for that of B. So B forms a basis for itself, and for A as well. I won't go into all the details of this proof. I'll just get a little bit of intuition here. This first part, if A and B are row equivalent, they have the same row spaces. Well, think about it this way. If the rows of A are linear combinations of the rows of B, well, sorry, if B is the row echelon form of A, well, then the rows of A are linear combinations of the rows of B. We used linear combinations of the rows of A in order to get to B. And we could do that in reverse. So that's also true in reverse. The rows of B are linear combinations of the rows of A. So they're row equivalent. Well, all these linear combinations of rows of A to rows of B is nothing more than the row space of each. So yeah, they have the same row space. Then each non-zero row of B is linearly independent with the rows above it. So this is pertaining to the bottom here. So so remember that if we look at maybe something like this, we look at this subsequent row, it is linearly independent of the row above it because its leading entry is in a different column than the previous row's leading entry, and it has a 0 here. So this, there's no way if we went above and had other rows above it following this echelon form, we could see that these things are linearly dependent. So there's further deeper arguments for that in the textbook as well. This is just intended to be a sketch of why these things hold. The critical one here, I think most useful one on this page is the following, right? The pivot columns of A form a basis for the column space of A. That's really useful. The other thought is this. If B is in echelon form, so if we take a matrix A, convert it to echelon form, then we can pick up the non-zero rows of its echelon form and we'll form the row space of A. That's the point of this theorem. So this tells us how to form the column space and the row space of the matrix. So let A be this 3x4 matrix. Once again, find a basis for the row space of A. Well, in the previous example, using this matrix, we had this echelon form. So now I'll just pick up all the non-zero rows of this matrix. It's first and second row. So we have this set is actually our basis. The row space of A, ooh, that's not good notation down below. This set here, really we should highlight it as follows. This set B is the basis for the row space of A. This is not true, but down below, it's a good error to dwell on for a moment. It's not true because this is just, on the right-hand side, it's just a set containing two vectors. It's not the linear combination of those vectors. So we have to be a little bit better with our notation here. And the row space of A is equal to the span of these two vectors. And now this is exactly true. But really, the better notation overall is just because this is the span of, or sorry, this is the span of vectors is the row space of A. It doesn't mean that we've given a basis. We're not writing it in a form that suggests it's a basis. It's probably better to go with writing our basis as this set. It's given right here. Here's our basis. We just pull our non-zero rows from row echelon form. We've got the basis we need. This is just maybe an extra sort of follow-up, sort of confirming the statement. So that's it. We've done it. We did a messy version of finding row spaces and column spaces and the null space, but now we've got some really nice tools for that, right? Remember, to find the null space, it's a matter of looking for free variables to know how many vectors you're going to have in the null space. But really, at the end of the day, it really just comes down to pulling the basic variable columns for that. So the column space was to find the pivot columns of each of the matrix A, and then the row space is to take the non-zero rows of matrix A in echelon form, and that will get you through essentially most of section 4.3. It'll be nice later on to see the rank theorem for matrices that will give us a good connection between all of these things. So we'll see that later on.